Hello. Today we are going to discuss Module 3 of CCNA7, Protocols and Models. My name is Kwame Nimapia. I'm a Cisco Certified Academy Instructor and the CEO for Kwaps Networks Training Academy here in Ghana. You can find our website on www.kntaga.org and our Facebook handle at Kwaps Networks. The model objective is to explain how network protocols enable devices to access local and remote network resources. So in this, we are going to look at the rule, which is the description of the types of rules that are necessary to successfully communicate. We're also going to look at protocols and explain why protocols are necessary in network communications. We're also going to look at protocol suites and explain the purpose of adhering to a protocol suite. And then we'll look at standards and organizations. Here, we're going to explain the role of standards organizations in establishing protocols for network interoperability. Then we're going to look at reference models and explain why the transmission control protocol, internet protocol model, and then the open system interconnection model are used to facilitate standardization in the communication process. Then we go on to look at data encapsulation, which will explain how data encapsulation allows data to be transported across the network. Then finally, we will explain how local hosts access local resources on a network. The rules. We'll look at communication fundamentals. Computer networks can vary in different sizes and complexity. It may not be enough to have a connection. Devices must agree on how to communicate. There are three elements to any communication. There will be the source, which will be the sender. There will be the destination, which will be the receiver. And there will be a channel or the media that provides the path of communication to occur. All communications are governed by protocols, and protocols are simply rules. So rules that communicate or communications will follow are what we call protocols. Now, these rules vary depending on the protocol. So when you look at the pictures here, you see that we have a human communication and an electronic communication. In human communications, you have the message source, like discussed in the previous slide, and that message source will have a transmitter that will transmit that message, and it needs a particular channel or medium for it to be transmitted. Now, when it gets to the receiver also receives the message as signal, and then it is decoded and then the receiver himself becomes the message destination. Here, in electronic communication or in computer communications, you still have the same rule applying here. You have the message source, you have a transmitter, you have a transmission medium, you have a receiver, and then the message destination. Now let's look at rule establishment. Now individuals must use established rules or agreements to govern the conversation. The first message, as you see on the screen, is difficult to read because it is not formatted properly. The second shows the message is properly formatted. So if you attempt to read this message, you see the difficulty because the messages are not properly, or the message is not properly formatted. And at even a point, you see that you have another language in the English language that was attempted to be used to deliver or to be used as the message. But when you look at it down, you can easily read rules govern communications between humans. It is very difficult to understand messages that are not correctly formatted and do not follow the established rules and protocols. The structure of the grammar, the language, the punctuation, and the sentence make the configuration humanly understandable for many different individuals. So when you have a good structure, when you have a good grammar, and then an understandable language, and then the correct punctuations, then it makes it it gives a human understanding, and many individuals can comprehend. Protocols must account for the following requirements. 1. The unidentified sender and receiver. 2. There must be a common language or grammar. So, if there is no sender or receiver, how will we have an effective information transmission? When there is no common language and grammar, you understand that when there is no accepted language, there cannot be comprehension. Because if one person speaks Swahili and the other person also understands English, the two of them cannot have a perfect communication. And therefore, if there is no accepted language or a common language and then grammar, it will not be possible to establish communications. Then the rules must also establish speed and timing of delivery. And then it must also establish confirmation or acknowledgement requirements. Common computer protocols must be in agreement and include the following requirements. There must be message encoding. There must be message formatting and encapsulation. There must be message size. There must be required message time. And then there must also be message delivery options. What is message encoding? This is the process of converting or turning information into another acceptable form for transmission. So you agree with me that electronic communication, for that matter, digital devices which process data, which process or understand information in zeros and ones, will have to modulate and demodulate the data that is leaving them so that the transmission medium can carry it in a format possible for it to carry it. And when it reaches its destination, it must also be able to demodulate the analog data that has gone through the transmission into a digital data for the receiving device to be able to understand. Decoding reverses this process to interpret the information. So here, you have a message source, and then the encoder changes the signal so that it can be transmitted on whatever transmission medium. So if the transmission medium carries the signal and then it reaches the receiver also decodes it into a format that the destination device can understand and interpret. Now, when a message is sent, it must use specific format structure. So we can use the post as an example. If you use the normal post, you encode a message, and that is equivalent to writing your thoughts on a sheet. Now, this message that has been encoded is kept in an envelope. So you buy an envelope and you put your message in that envelope, and then you wrap it, which we call encapsulation. So you see that the thoughts that have been expressed on this paper is put in an envelope. And on that envelope, there are certain information that are kept on that envelope so that there can be effective data transmission. You have the sender's address, and then you have the recipient address. So that in every process of the transmission, the one who is carrying this information that has been encapsulated into this envelope or wrapped by the envelope will know who the receiver is, which is the destination, and then we'll also know the source. We'll also know the source, who is the sender. So message formats depend on the type of message and the channel that is used to deliver the message. On the other hand, when you look at these, all these are salient information that are kept on an envelope to make sure that there can be effective transmission. So this is the format for physical post. And when you come to the electronic format, you have sizes for anything that are kept on an envelope, or sizes for anything that are kept on a particular message that is supposed to be sent in electronic transmission. So when you look at this, here you have the source address and the destination address, just like you have on the envelope, so that the computer that is sending or the transmission will know who is sending and who is receiving, and then so that it is sent to the right destination. And then you have payload length, you have next header, you have hop limit, you have flow label, you have traffic class, and you have version. All these are also information that are kept to aid data transmission. So we say that for the version and part of the class, it has to be 1 byte. So 2 bytes, 3 bytes, and then you have 4 bytes. And when you add all these things, it should be the maximum number of bytes for information that are kept on a frame that is supposed to be sent. So a whole frame that is supposed to be sent in the transmission medium must be 40 bytes. Message size. Now, encoding between hosts must be in an appropriate format for the medium. Messages sent across the network are converted into bits. The bits are encoded into a pattern of light, sound, or electrical impulses. So when you have one source sending information to the destination device, once it leaves this digital device and is supposed to be traveling on a transmission medium, it is converted from this device. There's a device that converts it into bits so that it can travel on this transmission medium. And then the transmission medium could be through a pattern of light, which is a fiber optic transmission or a fiber optic medium, sound, or electrical impulses. And for electrical impulses, it is the copper medium. So it could be either a coaxial medium, or it could either be a twisted pair medium, either shielded or a shielded twisted pair. And then it could also be through the air or sound medium. And any of these medium will see the data that's supposed to be sent on the medium being converted. Message timing. Message timing includes the following. We have flow control, which manages the rate of data transmission and defines how much information can be sent and the speed at which it can be delivered. Now, you also agree with me that even in human communication, when anybody has a communication with anybody, another person, and then that sender of the information speaks faster than the person can comprehend. Sometimes you tend to ask the person, "What did you say? Can you come again?" So there must be an accepted flow so that both devices can have the understanding at one time. So flow control is very important in human communication, at the same time in data transmission or electronic communication. So it is the management of the rate of transmission and defines how much information can be sent and the speed at which it can be delivered. And then we also have what we call the response timeout. Now, this manages how long a device waits when it does not hear a reply for the destination or from the destination. So if it needs a reply from the destination and then the reply is not forthcoming, it will have to wait for some time and decide either to truncate the connection or decide otherwise. And then we also have the access method. Now, this determines when someone can send a message. There may be various rules governing issues like collisions. Collisions are simply data crashes. Now, when data collide in a transmission medium, we call them collision. Now, even in our normal contemporary situations or human situations, when you have two cars crashing on the road, we say there has been a collision. So if it is anytime there is an accident on the road, for some time, because of the collision and then the repercussions of the collision, you realize that the cars that are traveling will have to park for some time for the road to be cleared before movement also begin again. So collision is one factor that impedes data communication or that impedes electronic communication. And access method should have rules that governs issues like that when the data crashes. And this is when more than one device sends traffic at the same time and the messages become corrupt, or when the messages collide. So some protocols are proactive and attempt to prevent collisions. Other protocols are reactive and establish a recovery method after the collision occurs. So we have rules that prevent data corruption, and we also have rules that establish recovery after the collision has occurred. Now let's look at some message delivery options. We have one-to-one communication, which we call the unicast transmission. We have one-to-many, which we call the multicast transmission, that are normally one to all. And then we have the broadcast, which is one to all. So here, a unicast message sends from one to one. Here, a multicast message sends from one to accession of what? The members. The broadcast sends from one to all. Some other literature may use what we call the node icon. And this is a circle that represents all devices. So these figures illustrate the use of node icons for delivery options. So here in unicast, the node icon shows from one to one, multicast from one to a section, and then the broadcast will show that it delivers this to all other members. Protocols. Now, network protocols define a common set of rules. They can be implemented on devices in either a software, a hardware, or both. Protocols have their own function. They have their own format, and then they have their own rules. So let's look at some protocol types. We have the network communication protocols, and what they do is that they enable two or more devices to communicate over one or more networks. We also have network security protocols, and these type of protocols secure data to provide authentication, data integrity, and data encryption. We have routing protocols that enable routers to exchange route information, that compare path information and select best path. And then we have service discovery protocols that are used for automatic detection of devices or services. So at every point in the network, we have a rule or we have a protocol that takes care of what should go on there. What are the functions of network protocols? Here, devices use agreed upon rules to communicate. So protocols may have one or many functions. So the functions of protocol is one, for addressing. Now, in addressing, it identifies the sender or receiver. So just like we saw on an envelope, there's a source and destination address. So in computer networks, the protocol should function by providing a source or providing rules for source and destination communication. So the sender and then the receiver. It should also have a rule on reliability. And in reliability, network protocols are supposed to guarantee delivery. Network protocols must also function in the area of flow control that ensures that data flows at an efficient rate. Network protocols must also function by controlling sequencing. And this is a unique label of each transmitted segment of data. They must also function in the area of error detection. And this is the determination if any data became corrupted during the transmission. And must also function in the area of application interface. Here, there is a process-to-process communication between network applications. So here, you see the sender here. The sender says that I will send this message across the network using an Internet Protocol version 4 header. Now, the communication devices or the routers here must also understand the protocol of Internet Protocol version 4, must understand it before they can also what? Accept it and then transmit it. So the router say that, oh, okay, I will forward it because I also understand. And then the receiver or the server here can also say, I also accept this message because I understand. So there's a level playground, or there's a common understanding of whatever is being sent. And when each of them understand each other, there's an effective data transmission. Protocol interaction. How do protocols interact each other at each layer of the data transmission process? Networks require the use of several protocols. Each protocol has its own function and format. So we have a protocol called Hypertext Transfer Protocol, HTTP. Now this protocol governs the way web server and a web client interacts. And they also define content and format. And then we have the Transmission Control Protocol, which we call the TCP. Now, this manages the individual conversions, it provides guaranteed delivery, and then manages flow control. We also have the Internet Protocol that delivers message globally from sender to the receiver. And then we have Ethernet Protocol that delivers message from network interface card to another network interface card on the same Ethernet local area network. So an Ethernet protocol is a local area network protocol. Now, we want to look at protocol suites. Now, protocols must be able to work with other protocols. So, a group of interrelated protocols necessary to perform a communication function is what can be described as a protocol suite. Or, they are a set of rules that work together to help solve a problem. So, the protocols are viewed in terms of layers. We have the higher layers, we have the lower layers concerned with moving data and provide service to upper layers. So protocol suites are a set of rules that work together to solve a problem. We want to look at the evolution of protocol suites. There are several protocol suites. We have what we call the Internet Protocol Suite or the TCP IP suite. Now, the most common protocol suite and are maintained by the Internet Engineering Task Force, IETF. We also have the Open Systems Interconnection Protocols, OSI. This is a protocol that is developed by the ISO and the International Telecommunications Union. We also have another protocol which we call the proprietary suite that are released by Apple Incorporated, and we call it Apple Talk. And then we have the Novell Network, that is a proprietary suite developed by Novell. So here, this is a TCP IP layer name. So for the TCP IP, we have the application, the transport layer, the internet layer, and then the network layer. And when we move on to subsequent slides, we'll understand what we mean by the TCP IP protocol, and then we will understand other types of protocols like the Open System Interconnection Protocol and know what goes into it. So here, at the application layer, the TCP IP protocol contains the HTTP, the DNS, the dynamic host configuration protocols, and then the file transfer protocol. And then for ISO, which is the International Standards Organization, you have these protocols here. For Apple, you have this protocol here. And then for Novell Network, you have these protocols. So at this layer, which is the transport layer, for TCP IP, you have the TCP and then the UDP transport layers. And then you have it for different protocols at the same level. And then the Internet Protocol, you have the IP version 4, IP version 6, you have the ICMP, and then ICMP version 4 and version 6. And then for the other types of protocol suites, they have theirs also respectively. And for the Network Access Protocol, for the TCP IP, for the ISO, for the Apple Talk and Novell, all of them use the Ethernet, all of them use the Address Resolution Protocol, ARP, all of them use the wireless LAN. The TCP IP protocols operate at the application, transport, and internet layers, like I explained earlier. So the most common network access layer LAN protocols are the Ethernet and then the wireless LAN. TCP IP is a protocol used by the internet and includes many protocols. We have the TCP IP, which is an open standard protocol suite that is freely available to the public and can be used by any vendor. It's also a standards-based protocol suite that is endorsed by the networking industry and approved by the Standards Organization to ensure interoperability. So the TCP IP protocol suite at the application layer has the domain name system and then the DHCP for host configurations. So you have protocols at the application layer, you have the DNS for the naming systems, and then for the host configurations, you have DHCP protocols that take care of that. For email, you have the post office protocol, and then the simple mail transfer protocol, internet message access protocol that also take care of emails. For file transfer, we have the file transfer protocol, we have the Trivial File Transfer Protocol, and SFTP, Simple File Transfer Protocol. And then for the web and web services, these protocols are also the HTTP, HTTPS, and then the rest also take care at the application layer where the user is. Now, when you come to the transport layer, we have the Transmission Control Protocol, which is connection oriented, and then we have the User Datagram Protocol, which is also connectionless protocol. And then when you come to the Internet Access layer, you have the Internet Protocol version 4, Internet Protocol version 6, and then you have Network Address Translation, which are for the Internet Protocol. And then for messaging, and Internet Control Messaging Protocol, version 4, version 6. And then you have the OSPF, Open Shortest Path First. For routing protocols, you also have Enhanced Interior Gateway Routing Protocol, which is a proprietary protocol for Cisco. And then you have the Border Gateway Protocol, which is also a proprietary protocol. And then when you come to Network Access layer, you have, for address resolution, you have the Address Resolution Protocol. And then when you come to the Data Link Protocol, we have the Ethernet, and then the wireless LAN. And these are the most common protocols for the Network Access layer. So the TCP/IP communication process. Now, a web server encapsulating and sending a web page to a client. So here, this is a web server. This is a web client. So the web client requests a web page, and then the web server is encapsulating it to be sent to the web client. When it has to encapsulate it, the data itself that are supposed to be sent, which is a user data, is there. And on the user data, we have all the protocols that will have to govern this user data to reach its destination. So this particular server is sending what we call an Ethernet frame. And this whole thing is what we call an Ethernet frame. And on the Ethernet frame, you need the protocols that will govern the data transmission. So the data itself is here, is within the Ethernet frame. And then the Ethernet protocol, which we have already discussed, the Internet protocol, and then the TCP protocol, Transmission Control Protocol, because the Transmission Control Protocol will take care of the data that is supposed to be transported from source to destination. The Internet protocol takes care of the addresses that are given as source and destination addresses. And the Ethernet protocol also takes care of data transmission within the LAN. So on a TCP/IP, so the server that is encapsulating and sending a web page will have to send the information with the protocols involved, so that they will take charge and make sure that everything is in place from source to destination. Now, when you look at this side, a client is de-encapsulating the web page for the web browser. So this server has sent the web page. It's getting to the client, and the client will also de-encapsulate it. That is, change it from this format to an understanding format for this client to interpret. So it encapsulated it in this form. When it goes to the transmission medium, the format is changed, or it is decoded, it is encoded, and the format changes to a transmissible format of zeros and ones. Now when it gets here, it must be de-encapsulated so that this device can also understand and interpret it. We want to look at standards organizations. Standards are specifications that will have to be followed by manufacturers to improve interoperability. When we talk about interoperability, we want to talk about the fact that different vendor components will be able to operate. That is why if you have a simple computer system, you can have a computer monitor, that is a Dell monitor, interconnecting a system unit that is an Acer system unit, and within that system unit you have the processor, that is an Intel processor or an AMD processor. You have a motherboard coming from another company, and all other components coming from different companies, but have been able to interoperate, and all these things can be possible through standard maintenance. So open standards encourage interoperability, it encourages competition, and then it encourages innovation. So we want to look at standard organizations, and these are organizations that maintain specific standards in specific areas, and they are vendor neutral. They are not or non-profit organizations. They are established to develop and promote the concept of open standards. The Internet Society is a standard organization that promotes the open development and evolution of the Internet. The Internet Architecture Board is also responsible for the management and development of Internet standards. The Internet Engineering Task Force develops, updates, maintains Internet and Tcp Ip technologies. And then the Internet Research Task Force, IRTF, is focused on long-term research related to Internet and Tcp protocols. So here you have the Internet Society, and under it comes the Internet Architecture Board, and under it you have the IETF, which also has the Internet Engineering Steering Group, and under it we have the Working Group, and then Working Group 1 and Working Group 2. And then at the other side of the organogram you have the Internet Research Task Force that also has the Internet Research Steering Group under it, and it also has Group 1 and Group 2. Now, standard organizations involved with the development and support of Tcp IP. The Internet Corporation for Assigned Names and Numbers, ICANN. Now, this coordinates IP address allocation and management of domain names and assignment of other information. And then we also have the Internet Assigned Numbers Authority, IANA. Now this standard body oversees and manages IP address allocation, domain name management, and protocol identifiers for ICANN. We want to look at standard bodies that also cover electronic and communication. We have the IEEE, Institute of Electrical and Electronic Engineers. These are dedicated to creating standards in power and energy, healthcare, telecommunications, and networking. We have the EIA, Electronic Industry Alliance. They develop standards related to electrical wiring, connectors, and then 19-inch racks used to mount networking equipment. We also have the Telecommunications Industry Alliance, TIA, which develops communication standards in radio equipment, cellular towers, voice over Internet protocol devices, satellite communications, and more. Then the International Telecommunications Union, Telecommunications Standards, defines standards for video compression, Internet protocol television, broadband communications such as digital subscriber line. We want to look at reference models. Complex concepts such as how network operates can be difficult to explain and understand. For this reason, a layered model is used. We have two layered models that describes network operations. We have what we call the Open System Interconnection Reference Model, OSI, and then we have the Tcp Ip Reference Model. So when you look at this, the OSI model is here, and then the Tcp Ip model is also here. With the OSI model, We have the physical layer, the data link, the network layer, the transport layer, the session layer, presentation, and application. And the TCP IP model is the network access model, the internet model, the transport, and then the application model. All of them have the TCP IP protocol suite running in them at each layer, and we will discuss. What are the benefits of layered model? Now, layered model assists in protocol design because protocols that operate in a specific layer have defined interface to the layers above and below. Now, layered models also foster competition because products from different vendors can work together. They also prevent technology or capability changes in one layer from affecting other layers above and below. And they also provide a common language to describe networking functions and capabilities. So the Open System Interconnection Reference Model, which is a 7-layered model, and then it is numbered from the down to the top. So it has the physical layer, which we normally call layer 1, and layer 1 describes the means to activate, maintain, and deactivate physical connections. We have the layer 2, which is the data link layer, which describes methods of exchanging data frames over common media. We have the third layer, which is the network layer, that provides services to exchange the individual pieces of data over a network. We have the layer 4, which is the transport layer, that defines service to segments, transfer and reassemble of data for individual communication. And then we have the session, which is layer 5, that provides services to the presentation layer and manages data exchange. The layer 6, which is the presentation layer, provides a common representation of data transferred between application layer and services. And then we have the layer 7, which contains protocols used for process-to-process communication. Now, one thing any student will have to understand, the OSI model reference starts its numbering from layer 1. So whenever we talk about layer 1, know that it's a physical layer, and then ends at layer 7, which is the application layer. Now, this is a theoretical model of layers that shows how data starts from source to the destination, and whatever happens to the data during transmission are explained at each layer of this model. So whenever you hear layer 3 protocol, layer 4 protocol, you have to know is network protocol or transport layer protocol. Now, normally you can also use mnemonics to remember these layers. In order to easily remember, you can use the first letters to form a mnemonic that will help you to easily recollect. For example, you can say please. For physical, you can say please do not throw sausage pizza away. So when you remember the please, you know that it's physical and it's at layer 1. When you remember the do, you know is the data link layer, not is the network layer, and then the transport layer, that is through, and then the sessions layer, which is sausage, and then the presentation layer, which is pizza, and then the application layer, which is away. So please do not throw sausage pizza away. And I remember those times when the Pope died. One of my students also used another mnemonic at that time and said that all priests saw the nice dead pope. All priests saw the nice dead pope. So it is only for you to also remember, if you do it the other way around, that all priests, so the all is the application layer at layer 7, so that you number them up. Tcp Ip Reference Model is a workable model. Now this model explains in layers what happens to data transmission through in networking. But this is not a workable model. This is a theoretical model that helps teachers to explain, that helps students to understand the data transmission process. But the workable model is the Tcp Ip model. And this model inculcates other models of the OSI model and is shortened. So it has only 4 layers, but at the end of the day, all the other layers have some of them brought together to form one layer. For example, the application, presentation, and session layer have been consolidated into one, and we call it the application layer for the Tcp Ip model. And then we have the transport layer, and then the transport layer is the same way, which has been maintained. And then we have the internet layer that consists of the network layer and then the data link layer. And then we have the network access layer that has the physical layer. So the application layer for the Tcp Ip model represents data to the user plus encoding and dialog control. And then the transport layer supports communication between various devices across diverse networks. Then the internet layer determines the best path through the network. And then the network access layer controls the hardware, devices, and media that makes up the network. So as you can see here, it's better compared here, the OSI model reference and then the Tcp Ip model. Now this OSI model divides the network access layer and then the application layer of the Tcp Ip model into multiple layers, like I explained earlier. Now the Tcp Ip protocol suite does not specify which protocols to use when transmitting over a physical medium. And then the OSI layers 1 and 2, which is the physical and data links layer, discuss the necessary procedures to access the media and the physical means to send data over a network. Data encapsulation. Segmenting is the process of breaking up messages into smaller units. Multiplexing is the process of taking multiple streams of segmented data and interleaving them together. Segmenting message has 2 primary benefits. It increases speed. So here, large amounts of data can be sent over the network without trying up a communication link. And then there's an increase in efficiency where segments which fail to reach the destination need to be retransmitted and not the entire data stream. Sequencing. Is the process of numbering the segments so that the messages may be reassembled at the destination. So TCP is responsible for sequencing and the individual segments. So sequencing are giving numbers of which one of them appear first and which one of them will be received first. And so when the data reaches its destination, they have to be reassembled according to the sequence numbers that have been given them. So the labeling provides for ordering and assembling the pieces when they arrive. Protocol data units, PDUs. Encapsulation is the process where protocols and their information encapsulation is the process where protocols add their information to the data. At each stage of the process, a protocol data unit has a different name to reflect a new function. There are no universal naming conventions for PDUs in this course. The PDUs are named according to the protocols and the TCP IP suite. So the PDUs passing down the stack are as follows. Now, bits. The protocol data unit, and we call it encapsulation. At layer 1 of the OSI model, which is the physical layer, it is the connection of devices, and the devices send data through cables, and these cables transmit information in what? Zeros and ones, and at that level we call them bits. But when they move up to the second layer, which is the data link layer, certain information are added to the bits, and we say there has been an encapsulation. So an encapsulation bit, or these bits, are put in an envelope to be sent, and these bits that are wrapped for the next level transmission. And when they get to the second layer of the OSI model, we say that they have been encapsulated. So they leave layer 1 to layer 2, and their encapsulated bits are called frame. Now when they move from layer 2 to layer 3, they are encapsulated frames, and at layer 3 we call them packets. So each layer and then its encapsulation of data that has to be sent. And then when it moves to layer 4, which is the transport layer, the transport layer does what we call the segmentations, the sequencing, and encapsulated packets are what we call segments. Now, from layer 4 to layer 5, the segments are presented, and we call it data. So from layer 5 to layer 7, the data stream is data, and there are no more encapsulations until they are de-encapsulated in the receiving network. A better explanation will be done in a lab. So encapsulation is a top-to-down approach or process where the level above does its process and then pass it down to the next level of the model. This process is repeated by each layer until it is sent as a bit of stream. So here, a bit of stream is supposed to be sent from the web server to the web client, and the data is encapsulated. This is the data. It's encapsulated with all the necessary information, the TCP protocols, the internet protocols, and the Ethernet protocols. All of them have been wrapped and added to the data to be sent to the next level of the layers in the OSI model. And de-encapsulation. Data is de-encapsulated as it moves up the stack. So it means that a typical example is in human communication is when you have written a letter and then you put the letter in an envelope. We say that you have wrapped the letter and we call it encapsulation. And then you put source and destination information on that envelope. Now, when the envelope goes through, goes to the post office and the post sends the letter to the receiver. Now, when it is represented to the receiver will tear up the envelope and remove the letter. And that is an example of a de-encapsulation. So when data is encapsulated to move up the ladders of the transmission medium, when it reaches the presentation point, the receiving device will also have to de-encapsulate it. That is removing all the wrap. So this is the data which have been encapsulated with all these information so that they can guide the data transmission. But the most important thing is this data. So the data, that one that has been sent here, when it comes from the web server to the web client, when it gets to the web client will remove all these information, leaving the data itself so that it can interpret the data. So when a layer completes its process, that layer strips off the header and passes it up to the next level to be processed. This is repeated at each layer until it is a data stream that the application can process. So you have data set. So you receive, the first one is bits which are received, and then it moves on, it's encapsulated into frames, and then it is encapsulated into packets at the next level because other information are added for the next level transmission. And then it goes to the transport layer, layer 4, which is the segment layer. And at layer 5, it is encapsulated as data stream. Now, when it is supposed to be presented at the presentation layer, then before at the application layer, which is layer 7, it is received, from layer 5, it is de-encapsulated. So all the information that are added will also be removed so that it can be what? Well interpreted and understood by the receiving device. Data access. Both the data link layer and then the network layer use addressing to deliver data from source to destination. The network layer source and destination address are responsible for delivering the IP packet from source to the final destination. And then the data link layer, which is the layer 2, source and destination address are responsible for delivering the data link frame from one network card to another on the same network. So this is the OSI model. This is layer 1, layer 2, layer 3, and layer 4, and these are the upper layers. At layer 1, which is the physical layer, there is timing and synchronization of bits. When these bits are encapsulated into frames, which is layer 2, at the data link layer, destination and source physical addresses are added so that when it's supposed to be transmitted by the network layer, it will know where the data is coming from and where it is going. So here, the destination and source physical addresses are added for the next transmission. and these are also added to the frame. So encapsulated frame becomes packet at layer 3 of the OSI model, and at the network layer, which we also refer to layer 3, the destination and source logical network addresses are also added. And then when they are added, these are information that are important for the transport layer to transport, and therefore these destination and source logical addresses, which are the IP addresses that are added, are also, and then it moves to the next layer, which is the transport layer, and we call it a segment. And here the destination and source process numbers are added for transport. And when it moves to the upper layers, which is layers 5, 6, and 7, there is encoded application data. Now, the source IP packet contains 2 IP addresses. The source IP address, the IP address of the sending device, original source of the packet. And then the destination IP address is the IP address of the receiving device, final destination of the packet. These addresses may be, so the source IP, and then the destination IP is the server. So this is the source, and then this is the destination IP address. So at layer 3, the IP packet, because at layer 3 of the OSI model, the encapsulation unit is packet. So these routers can be found at layer 3 of the OSI model, and what they forward are packets. So when it leaves the original source, before it reaches these routers, it starts from the original source as bits, and this is layer 1. It moves through the cables as bits of zeros and ones. Then it moves to layer 2, which we call the frame. So when it moves to layer 3, it becomes packets because they are encapsulated frames. And routers forward packets. So the destination address is 172.16.1.99, which is the server. And then the source address is 192.168.1.110, which is the what? The sender. So if you want to relate this to the normal post, the address of the recipient is on the envelope, and then the address of the sender is normally at the top left corner or at the back of the envelope to show who is sending the letter and who should receive the letter. So layer 3 logical addresses, and at layer 3 we have the IP addresses. An IP address contains 2 parts. The leftmost part of the IP address indicates the network group which the IP address is a member. So we have 2 versions of the IP addresses. We have the Internet Protocol version 4 address, and then the Internet Protocol version 6 address. Now each local area network or wide area network will have the same network portion. Now the host portion for an IP version 4, now the remaining part of the address identifies a specific device within the group. So this portion is unique to each device on the network. We want to look at devices on the same network. When devices are on the same network, the source and destination will have the same number in the network portion of the address. So here, PC1, 192.168.1.1. If both the source and destination are on the same network, you see that the first 3 network portions are the same. So it tells you that this class C address, 192.168.1.1, which is the source, and then the 192.168.1.9, which is the destination address, both source and destination devices are on the same network, because the first 3 portions which were taken by the network are the same. So this is only signifying that on this same, the first device has a number of 110 or 110 hosts, and there are other destination devices. Data link, the Ethernet frame header, have a MAC address, and this is the MAC address of the destination device, CCCCCC. And MAC addresses are 12 hexadecimal numbers that shows a particular device. These numbers are bound in the network interface buffer that shows the identity of the devices, and the first 6 represents the manufacturer, and then the last 6 represents the host itself. So every networking device that is a member of a network has a media access control address. So this MAC address for the server, and this is the MAC address for the source device. And apart from the MAC addresses, they also have Internet Protocol addresses that also uniquely identify them. Role of the data link address on the same IP network. When devices are on the same Ethernet network, the data link frame will use the actual MAC address of the destination network interface card. So MAC addresses are physically embedded in the Ethernet network interface card and are local addressing, as explained. The source MAC address will be that of the originator of the link, and then the destination MAC address will always be on the same link as the source, even if the ultimate destination is remote. So here, the source, this is the source MAC address. This is the source IP address. And then this is the destination MAC address. And this is the destination IP address. And that is what is denoted in this table. And all these information are added to the data and wrapped with the data, so that in the transmission, any device that picks the data and has to also work on it will also know where the source is coming from and then the destination that it has to forward. Now, when we look at a device or devices in a remote network, what happens when the actual destination or the ultimate is not on the same local area network and it's remote? What happens when PC1 tries to reach the web server? So here, the source and the destination MAC address, here, these ones, the PC1 and then the destination addresses are all on the same network. But when PC1 wants to reach the server, it means that it is going out of this network into another network. And we want to see what happens. That means that if PC1 tries to reach the web server, which is this web server, then it will have to go through this layer 3, and then the addressing must be well defined. Now, when the source and destination have a different network portion, this means that they are on different networks. For example, 192.168.1 and 172.116.1 are different classes of IP addresses. So this is the devices that use this particular address and devices that use this address are on completely different networks. So here, PC1 and this one may be on the same network, but PC1 and then the server are on different networks. So PC1 has a source MAC address as source IP address as 192.168.1.110, and then a destination address of 172.16.1 means that this server is on a different network to this particular source IP address. We want to look at the role of data link layer addresses on different IPs. Now, when the final destination is removed, layer 3 will provide layer 2 with the local default gateway IP address, also known as the router address. So the default gateway is the router interface IP address that is part of this LAN and will be the door, the gateway to all other remote locations. All devices on the LAN must be told about this address in their traffic, or their traffic will be confined to the LAN only. Once layer 2 or PC1 forwards to the default gateway, the router then can start the routing process of getting information to the actual destination. So here, when we talk about a default gateway, it is the router interface. So this router's interface here, which has been given an address of 192.168.1.1, becomes the gateway for these hosts to be able to reach other networks. So if these hosts, this server and these hosts are not told of this gateway, their data that has to be sent will be confined to this network alone, and they will not know which gateway to use into the internetwork. So all devices on this LAN must be told of this gateway, so that if they want to send any information, they will have to use this gateway. So before any host here is able to reach this web server, which is on a different network, has to use this default gateway, otherwise they cannot reach this network. Now the data link address is local addressing, so it will have a source and destination for each link. The MAC address of the first segment is this. This is the MAC address of the first segment, which is the AAAAA. So PC1 sends the frame to destination address, which is R1, which is the gateway, and the gateway receives the frame. Note, while the layer 2 local address will change from link to link or hop to hop, the layer 3 addressing remains the same. So this layer 2 address, as soon as it reaches here, the data that is being sent reaches here, it changes into packets, which is encapsulated frames. So switches forward frames and then routers forward packets. So frames can be found in layer 2 of the OSI model, so switches are found in layer 2. And then cables that send bits of data are found in layer 1, which we call the bits. And in layer 2, the switches will forward frames, and when it moves from the switch to layer 3, and layer 3 encapsulates the frames into packets. Now, while the layer 2 local addressing will change from link to link or hop to hop, the layer 3 addresses will remain the same, because at layer 3 you have the router's addresses, and then they will remain. Data link addresses. Now, since the data link addressing is a local addressing, it will have a source and destination for each segment, or hop of the journey to the destination. The MAC addressing for the first segment is the source PC, and then the network interface card of the PC will send a frame to the destination, which is the first router. This is the first router network interface card that will receive the frame. Now, if this router will want to send that information, it will what? It will encapsulate the frame with the information of the next hop. And then when it encapsulates it, we call it packet before it can send. So layer 2 destination network card, and then a source network interface card. Now the MAC addressing for the second hop is the source. The first router exit information sends the frame. So this router exit information will also send a frame, and then the destination router will also receive the frame. So it starts from here, and it starts from the the local network, and then it moves to the first router, and then the default gateway accepts the frame, and then also gives it to its exit port. That will also have to forward it from its port to the next port of the receiving router, which is the second router. So the MAC addressing for the last segment is that the second router's exit interface, which is here, sends the frame to the networking card of the server. So notice that the packet is not modified, but the frame is changed. Therefore, the layer 3 Internet Protocol address does not change from segment to segment like it changes at layer 2 MAC addressing. Now, the layer 3 addressing remains the same since it is global and ultimate destination is still the web server. Okay, so we have come to the conclusion of Module 3, and we have discussed the rules that a protocol must have a sender and a receiver. Protocols must include requirements as message encoding, formatting and encapsulation, size, timing, and delivery options. And then we have talked about protocols, and we say that to send a message across the network requires the use of several protocols. Each network protocol has its own function, format, and rules for communication. We also have protocol suite, or we have also discussed protocol suite, and we say that a protocol suite is a group of interrelated protocols, and Tcp Ip protocol suites are protocols used today. We've talked about standards, organizations, and we've talked about open standards as encouragement for interoperability, competition, and innovation. And then reference models, which are two models used in networking, which are the Tcp IP and the OSI model. We've talked about the Tcp IP model, which has 4 layers, and the OSI model, which has 7 layers. We also talked about data encapsulation, and we said that the form that a piece of data takes at any layer is called protocol data units. There are 5 different PDUs used in the data encapsulation process: data segment, packet, frame, and bits. We also discussed data access, and we said the network and data link layers are going to provide addressing to move data through the network. So the layer 3 will provide IP addressing, and layer 2 will provide MAC addressing. The way these layers are handled, or the way they handle addressing, will depend on whether the source and the destination are on the same network or are on different network. Thank you so much.